In last lecture, we discussed the properties of conductors in electrostatic equilibrium. Now let's move on to another kind of materials, dielectrics. Dielectrics are non-conducting materials in which electrons are bound to atoms and could not move freely in the materials. For example, glass and plastic. So how about the behavior when the external field is applied on the dielectrics? Let's explore it from an atomic view. We start with a water molecule. Please look at this figure showing the geometry of the water molecule. The oxygen atom is bonded to the two hydrogen atoms. An angle is formed between the two bonds. We notice that the center of the negative charge is near the oxygen atom, while the center of the positive charges is located at a midpoint along the line joining the hydrogen atoms as labeled by a cross. In this case, we say a molecule is polarized because a separation exists between the center of the negative charges and that of the positive charges. In some molecules, such as a water molecule, the polarization is always present. Such molecules are called polar molecules, while molecules that don't possess a permanent polarization are called non-polar molecules. We could model the water molecule and other polar molecules as dipoles because the average centers of the positive and the negative charges could be modeled as point charges. So let's study the behavior of the dipoles in the electric field first. Now suppose an electric dipole is placed in a uniform electric field E and makes an angle theta with the field as shown in the figure. Please note that the field is established by some other charge distribution excluding the dipole. Here the charges are separated by 2A. The electric dipole moment P is directed along the line joining the charges from -q to +q. Hence, the electric dipole moment has a magnitude of 2aq. Obviously, the electric force acting on the two charges are equal in magnitude and opposite in direction. Therefore, the net force on the dipole is 0. So, for the system composed of these two charges, the center of mass must have 0 acceleration. On the other hand, we could also study the dipole as a model of the rigid object under a net torque. Let's analyze the net torque on the dipole. By applying the definition of a torque about an axis, tau equals cross product of the vector r and the force. The vector r refers to the position vector of a point of application of the force relative to the axis. So the torque due to the electric force on the positive charge about an axis through O has a magnitude Fa sine theta, where the product of A and sine theta is called the moment arm of the force about O. We could see this force tends to produce a clockwise rotation, causing the dipole moment to align with the external field. By using the right-hand rule, we know the torque is directed into the page. We have the same effect for the negative charge. Therefore, the magnitude of the net torque about O is 2Fa sine theta, considering F equals QE and P equals 2aq, we can express the net torque tau as Pe sine theta. Based on this expression, it's convenient to rewrite the torque in a vector form as a cross product of the vector P and the vector E. Based on the electric behavior of the dipole, we firstly consider a dielectric made up of polar molecules placed in the electric field between two parallel plates. As shown in the figure A, the dipoles are randomly oriented before applying an external field due to the thermal motion. When an external field E is applied by two parallel charged plates, a torque is exerted on each dipole in the material. As discussed earlier, the dipoles tend to align with the field under the action of the net torque, as shown in the figure B. In such a case, the dielectric is said to be polarized by the field. Noting that in the interior of the dielectric, a positive charge of a dipole will always be cancelled by a negative charge of an adjacent dipole. We could find the cancellation does not occur at the two surfaces because there are no adjacent dipoles. Thus, the left surface of the dielectric carries a net negative charges. Similarly, the right surface carries a net positive charges. These charges are called induced charges. The induced surface charges on the two faces of the dielectric create an induced electric field represented by E. E is directed opposite to the external field E0, but with a smaller magnitude. However, the alignment is not complete due to the random thermal motion. The degree of alignment of the molecules with the electric field depends on the temperature and the strength of the external field. In general, the alignment increases with decreasing temperature and with increasing electric field. Now, let's study another kind of dielectrics, which consists of non-polar molecules. Please look at this figure. Such symmetric molecules have no permanent polarization, which we call non-polar molecules. When the external field is applied, what happens to the non-polar molecules? From this figure, we find that the electric force acting on the positive charge is directed to the right, while the force acting on the negative charge is directed to the left. Thus, the external field causes the center of the negative charge distribution to shift to the left relative to that of the positive charges, leading to a separation between two centers. Thus, a dipole is induced by the field. In this case, we call it induced polarization. This figure shows a net effect of the electric field on the nonpolar molecules is the same as that on the polar molecules. That is, the charges with equal magnitude and opposite sign would be induced at the two surfaces of the dielectric due to the polarization. Based on the studies above, we consider a slab of dielectric material placed between a uniform electric field E0 created by two parallel charged plates. Let's look at this figure. The electric field due to the plates is directed to the right and polarizes the dielectric. The net effect of polarization on the dielectric is the formation of an induced net positive charges on the right surface and negative charges of equal magnitude on the left surface. The induced surface charges on the two faces of the dielectric build up an induced electric field E opposing the external field E0. Therefore, the field in the dielectric is smaller than the external field, but not B0, since the magnitude of the induced field is smaller than that of the external field. So the net effect of the dielectric is to reduce the electric field. Now, please recall a conductor in a field. Here, if we replace the dielectric with a conductor, the net field between the plates would be zero because of electrostatic equilibrium. This is the difference between the properties of a conductor and a dielectric in the electric field. Before the end of this lecture, I would like to talk about one more thing: potential energy of an electric dipole. We identify the dipole and the electric field as a system. We determine the potential energy of the system as a function of the dipole's orientation with respect to the field. Similar to the potential energy of a charge field system, we could find the change of the potential energy of the system by evaluating the work done by an external torque when the dipole rotates from an initial orientation to a final orientation. The dipole moment vector becomes less aligned with the field under the action of the external torque. Suppose the kinetic energy of the system keeps constant. The amount of the work is then stored as the electric potential energy in the system. By definition, the work required to rotate the dipole through an infinitesimal angular displacement d theta equals tau d theta. We substitute tau by Pe sin theta and have this one. For a rotation from theta I to theta f, the change in the potential energy of the system is obtained by integrating this one over the limits from theta I to theta f, as expressed by this equation. We could determine the potential energy of the system when take the value of the potential energy to be 0 at some reference angle. It's convenient to choose theta I to be 19 degrees so that cosine theta I equals 0, and also choose the potential energy to be 0 at this initial orientation. Thus, we can have this expression, U equals minus Pe cosine theta. We rewrite this equation as a product of the vector P and the vector E for the potential energy of a dipole in the electric field. From this equation, it's obvious that the potential energy of the system reaches minimum when the dipole moment has the same direction as that of the external field. That's why the dipole will be aligned with the field when a field is applied. We have explored the electric properties of a conductor and a dielectric in the electric field. Next, I'll introduce a device called capacitor, which is composed of two conductors and a dielectric between them. See you next lecture.